Chapter 14, Section 11, Nitrate Reduction and Denitrification. Okay, we're going to be looking at inorganic nitrogen compounds. Okay, these are compounds that have nitrogen associated with them. All right, they are not going to be organic, meaning they are carbon-based. So they're going to be other compounds that are found in the environment. We have to keep in mind, we always seem to think carbon, the organic molecules, getting at the carbon-carbon bonds, so the energy there, stripping out the hydrogens, there's the energy, and only the energy. And that oxygen has to be the final electron acceptor in, cellular respiration. And no, it's not. That's not the case. That's not the case of the majority of living cells out there. It's the ones we study the most because it's the ones closely resembles what we are. And that's in our hubris we seem to think this is the most important. And no, it's not. When we look at the prokaryotes, we're going to see that a common alternative is nitrate. Nitrate is a good, will accept the hydrogens or will accept the electrons. Can be reduced, nitrate to nitrite. And then it can be further oxidized or reduced to other compounds, such as nitric oxide, nitrous oxide, dinitrogen, N2 gas. This is what is referred to as the denitrification. If you're going to take ammonia to nitrite, nitrate, and then you're ultimately going to end at dinitrogen, N2 gas, this is what is referred to as denitrification. So denitrifying bacteria, you're going to break down everything, releasing nitrogen gas as a final step. Not all bacteria can do this. Not all bacteria can do the complete thing. Most of those that can utilize nitrogen from the environment in this method can only do so part ways. E. coli is a great example. It can do nitrate reduction, but it can't carry it all the way out to releasing gas. That's going to be something like Pseudomonas that can do all the steps. We have to keep in mind that, we spend a lot of time talking the organic compounds, but in that functional group of organic compounds, the NH2, there's a lot of energy there. You look here, table 14.3 showing the oxidation state of that nitrogen, organic, the ammonia, functional group, oxidation state of -3 compared to nitrate or nitrite, which is +3, +5. So going from one to the other, organic, breaking it down, converting to nitrate, nitrite, well, there's a lot of energy to be had there that can be gained in this system. And when you're looking at this reduction of nitrate, nitrate, nitrite, nitric oxide, nitrous oxide, dinitrogen, N2 gas. Well, as I said, not all bacteria can do this complete process. Here we're looking, E. coli can only go from nitrate to nitrite. We saw that a couple of sections ago. And this is going from NO3 to NO2 is a very low energy yield process. But genus Pseudomonas, some of the species within the genus Pseudomonas can go nitrate and end at the N2 gas, and in the process there's a little higher yield of energy from the electrons that can be pulled out of this, from the hydrogens that can be pumped, and the ATP that can be synthesized from this. We're looking at the group of what are known as proteobacteria. Okay, these are going to be facultative anaerobes, meaning if oxygen's there, they'll use it. If it's not, that's cool. They can use something else too. They have other electron acceptors, such as iron or other organic or inorganic compounds that can be done in an anaerobic state. Now, this denitrification is detrimental for agriculture because remember they're spraying nitrite compounds onto their fields to add nitrogen back into the soil, which some of the other microbes can utilize and stuff like that. Well, if you get these denitrifiers, going to work, they're taking whatever the farmer's spraying and they're going to break it down, releasing it as either N2O gas or N2 gas. So it's not even going to be there and available for the plants anymore. Now, it's not completely, oh my gosh, we need to get rid of these guys, because we are also finding that these are beneficial, again, in sewage treatment. If you can take some of that nitrites that are in, local waters, in local, sewage systems, and if you can get it to the point where it's going to release the N2 gas, then, we don't have to spray potentially harmful chemicals. Again, we're going to see some form of electron transport chain. Okay. First step, nitrate reductase is going to kick off the process. This denitrification, remember I just said in the last slide, is subservient to the availability of O2. If O2's there, you're going in a different different metabolic methods. If O2 is lacking, then we're going to be doing this denitrification. And so what we find here is instead of the enzymes being turned on, turned off, it's the synthesis, the transcription translation level control, in the presence, absence of oxygen. But it's not just, is oxygen high level, low level? Their nitrate also has to be present. O2 levels are low, opens the door for the possibility for all of these denitrifying enzymes, this pathway, to be expressed. But if nitrate's not there, why bother? So, O2 levels, nitrate give us our control mechanisms. We've studied E. coli, Paracoccus, Pseudomonas, as I said in the last couple of slides. This proton motive force that will be, established due to this nitrification is going to go for the synthesis of ATP. Now that ATP that's synthesized is generally not for general cellular metabolism. This is going to be for the fixation or other processes. Not all of it. Some of it will be utilized, by general cell metabolic needs. So what do we look at here? This long process. Nitrate to nitrite to nitric oxide, nitrous oxide to nitrogen gas. Starts back here, NADH, giving up an electron, pumping some hydrogens, and you get an electron passing through. This electron passing through is going to aid in the nitrate reductase complex. So it's going to take nitrate, turn it into nitrite. The nitrite converting, using the NO2 reductase, which has an electron, a still slightly high energy electron powering it. Some of these electrons coming through. Some is going to power this, NO2 to NO. Some of those electrons are going to keep going through, pump some hydrogens, NO2, boom, to here, N2O, to gas. Here's the final electron acceptor, is going to be right here, NO2 and water.